So my research focuses on micas, which are these little platey layered minerals up in the corner there. And they're not the most abundant mineral in the Earth's crust, but they are one of the most important, if not the most important, when it comes to the strength and deformation of the Earth's crust. And that's because they're one of the weakest minerals. So when you have a system with lots of different components, physically, and you start to deform it under stresses, the weakest component is the one that naturally takes up most of that strain. So when rocks deform, we think about them cracking and breaking, and that's certainly what happens near the surface. But when you get deeper into the Earth's crust, the higher temperatures and pressures mean they actually deform plastically or viscously. And so we have to think about different mechanisms other than just cracking and breaking as to how they deform. So in most minerals, most of the ones you've studied, the most common way that they deform is this thing called dislocation creep. So you can imagine a crystal lattice, and it's a little tiny defect, point defect that just moves through the lattice, breaking one bond and reforming another, and it can do that in lots of different planes and orientations, so you get you can enable quite complex shape change. But that mechanism that we understand throughout minerals it falls flat with micas because of the layered structure of micas. So these dislocations can move across the layers, but they can't jump the layers, which means you can only deform by dislocation creep in one plane, and that doesn't fit for most natural systems. You need to be able to deform in lots of different planes to make a shape change. So we've kind of got this problem. We don't really understand the mechanism by which micas deform. They don't fit the previously decided model. Now recently, materials scientists in the last couple of years have come up with a new type of mechanism for layered materials, which is something called a replication. And it's essentially, so this is in a layer here, a layered material, or mica. It's essentially a ripple on the atomic scale that can move through the material. And this is important because while you can move it through in the same way as a dislocation on the planes, you also have this bending, which means you have some deformation in the other plane. So it can solve a lot of the problems associated with mica deformation. In my research recently, we believe we've found the first evidence of these mechanisms, these replications in natural minerals. And so this image here, that's 50 nanometer scale bar, so it's a bit dark, but that scale bar there is 1,000th of the width of a human hair. And what you're looking at here, again, it's quite dark, but these are individual layers of atoms and part of the lattice planes within the mica structure. And you see this curvature and deformation and destructure that we see here can only really be explained by replications, not by dislocations. So the implications of this new mechanism and the evidence we found for it is huge because it changes the way we model and understand the deformation of these important layered minerals in the crust, which has implications for the deformation of the whole of the Earth's crust, but also away from the environmental sciences. If we can prove their existence in nature, then they are apparent to lots of engineering materials, such as graphene and superconductors, which are also layered materials too. Thanks. Cheers.